Hi! Today we're going to learn about the direct comparison test. So let's say we have a problem like this. Is A, the series from n equals 1 to infinity of 1 over n squared plus 2 convergent or divergent, and B, the series from n equals 1 to infinity of 1 over n minus 5. Is that convergent or divergent? So before we start, let's first look at a graph. Let's say that we have this random function and let's say that we want to figure out whether the area under this function is convergent or divergent. So we're taking a step away from series and we're going to the area for a second. Now let's say we didn't know exactly how to compute the integral of this function, but we knew that there was a function that was greater than this function always, but still monotonically decreasing and approaching 0. So it has to be greater than this function for all values of x. It has to be positive and monotonically decreasing. And let's say that we know that the area under this curve is finite, and it comes out to be a value. Well, if we know that the area under this curve is finite and comes out to be a value, then the area under this curve on the same interval has to also be finite, because if we're just subtracting something from a finite value, subtracting something positive from a finite value that we know, then that means that the remaining area also has to be a finite value. So the same thing goes for series. Let's just look at it another way. So let's say once again we have these same two functions. So first, let's say we have this function again. And then let's say that we have once again that monotonically decreasing positive function that is greater than this function. So as you can see, this function is going to approach 0 because it's monotonically decreasing and it's positive. So if we add up all these values, and we want to find out whether this series from, let's say, here to infinity is convergent or divergent. So let's say that we don't know how to do that for this particular function. But we do have this function above that we know that even though it goes to infinity, all the values on it add up to a finite value. Well, if we know that, then we can say that this function here, that is basically bounded by this upper function, the x-axis, and the left and the right bound, one of which is infinity. So then we can say that this function on that interval also has a convergent series. Because, once again, we had that area graph, because we have this function, and we know it's finite, and we're subtracting values, these y values here, we're subtracting. So if we're subtracting values from a finite number, then that means that this also has to be finite. So when you add this up, it also has to be finite. So this shows how you can figure out, using a direct comparison test, whether a function is convergent. So this is known as the direct comparison test. So let's look at another example of the direct comparison test. So let's say that once again we have this graph, but this time the function looks like this. Or sorry, let's redraw that one. I meant to draw that differently. let's say this time the function looked like this. And we wanted to figure out whether this series was convergent or divergent from, let's say, 1 to infinity. So how do we do that? Well, let's take a look back at area. So we have this area that we don't know. And it goes to infinity. Now let's say that we had this other function that came like this. And we do know that on this interval from 1 to infinity, this area is divergent. Now, if we know that this area under this curve is divergent, let's say it's f of x, and this is g of x. So if we know that the area under f of x is divergent, then that means that the area under g of x is also divergent. Because when adding a value to a divergent area, the result also has to be divergent, because we don't know what type of infinity it is. Because divergent just means that in this case, the area would be infinity. But infinity can do many things. So the same thinking applies to series as well, as you saw in the last problem. So if we have this function g of x, and we have another function f of x, and f of x is bounded by, or is smaller than g of x for all x, but positive, and the series is divergent of f of x, then that means that the series of g of x on the same interval is also divergent. So let's try problem A and problem B. So in problem A we have 1 over n squared plus 2. So what function would be used to make a direct comparison test to? Well, let's use a parent function, because that seems like the easiest way and most practical way to go. So we have 1 over n squared plus 2. And then we have the parent function 1 over n squared. So which one is greater and which one is smaller? So because n squared plus 2 has a bigger denominator, then that means that it's the smaller function. Because we know that fractions with a bigger denominator are smaller. So that means that 1 over n squared from n equals 1 to infinity is going to be greater than or equal to 1 over n squared plus 2. And actually it'd just be greater than. The same direct comparison test holds true if it's greater than or equal to. So, now that we know which one's greater than and which one's less than, we can figure out which part of the direct comparison test to try. So we know that the function that we're looking at is less than the parent function. So we should try and see whether the parent function is convergent, because this function would look like this if it is convergent. So if the parent function was convergent, then that would mean that this function that we're trying to figure out is less than the parent function, but it's still positive from n equals 1 to infinity. And that means that it would have a finite, or it would be convergent if this parent function was also convergent. So let's figure out whether 1 over n is convergent, or 1 over n squared is convergent. So we do know that 1 over n squared is convergent because it is something that we should know. So because 1 over n squared is convergent, and because it's monotonically decreasing and positive, then that means that this function is also convergent. So this is the first application of the direct comparison test. Let's just erase the question mark and then box the convergent. Now let's move on to problem B. So in problem B, let's figure out the function and the function that we want to make a direct comparison test to. So the function is 1 over n minus 5. The parent function would then be 1 over n. So 1 over n minus 5, because it has a smaller denominator, must be greater than 1 over n. Now we know that 1 over n is a divergent series because it's a harmonic series, and the harmonic series is divergent. So this is divergent. So because the harmonic series is positive, it's monotonically decreasing, and it's divergent, and because it's less than this function that we're looking at from n equals 1 to infinity, then according to the direct comparison test, this function must also be divergent. So the answer to problem B is divergent. Today we learned about the direct comparison test in calculus. Thank you for watching this video.